So yeah, just right on time. I will start my short talk about the keyword final and how we're using it. So I'm happy to be back again this year, and great to see so many people still being active here at that time of the day. Okay, it depends on where you are on the earth, but probably many of us are. It's quite late already, but great to see and hear you. Um, yeah, so short talk about how we are using Final and how it turned out that it's for our use case. Some now and then it might be quite useful. Yeah, some words about myself. I'm basically a passionate software developer, C++ developer. I've been working quite a bit on C++ simulation models in the automotive industry, and now I'm working on those autonomous mower at STIHL. And some now and then I'm giving some lectures on software development here at Stuttgart. Um, yeah, and let's shortly start about how we are structuring our software. It's a bit simplified view on how we're doing it, but I think it it gets the basics. So roughly, our application, maybe many of you have a similar pattern. We on the one hand have some low-level drivers where we're accessing our hardware, and we have some higher level applications, and the application somehow uses the drivers, and we have this distinction. On the one hand, the top level, the applications, and those layers, they can be tested without any hardware dependencies, and our drivers there, we have the hardware dependencies. We have to get on real hardware to test those, but whenever possible we try to establish a layer where all applications or everything above the drivers can be unit tested. Um, and here in our case, the situation was we had the dependencies between the drivers, and this was quite performance critical. Now there we have a 200 kilohertz interrupt, and we really have to take care to optimize whatever happens there within those two drivers. Um, Now I want to dig a bit deeper and give you a rough estimate or a rough overview of how we are structuring our classes. So here a class diagram of this simple example. So basically what we are doing, we're having our applications, and they our drivers here at the bottom, and we're using abstract base classes for both drivers, and they implement those functions. Yeah, and here the main reason why we're doing it, to have it test to be able to test all our applications or all layers above the drivers easily, so we can provide fakes which implement the interfaces, and then we can test our applications. And now the interesting part was here this connection. So what we are doing here, our driver B has a dependency on driver A in that example, and we're doing some kind of dependency injection. So driver B knows about driver A, and other than the application, it knows driver A directly. So it does not take the path about via the interface, as we're doing it here for the application. The application gets driver A only via the driver A interface, but driver B gets dependency to driver A directly. Um, and as mentioned already, that's quite performance critical here. And it turned out we want to keep that, the approach with our abstract base classes, our interfaces. And here the simplified example from Compiler Explorer. We have our interface for driver A. Driver A implements that interface, and driver B uses driver A directly for some simple update call here. It accesses driver A, and does something with the result. Okay. And unfortunately, we here have a virtual function call to driver A. Although it's known directly, in our case, and in that simple example here, in our case, the compiler was not able to optimize that, to remove the virtual function call. And we've seen that due to our runtime. Our setup was not as simple as that one, so we had multiple compilation units and different dependencies here. But basically, the core setup boiled down to that one. And in the end, we came up with the solution that we just made our implementations final. And that simple step, making driver A final, turned out now driver B still the same dependency injection, the same approach of having abstract base classes to test our applications, but only making driver A final for us turned out that here the compiler on our setup was able now to devirtualize the function calls to A. And now we somehow have the best of both worlds. So when going back to our slide with the class structure here, we still have application A and application B getting their drivers or their dependencies via abstract base classes, via interfaces, so we can test them easily. But here, wherever it's performance critical, we can say, okay, driver A, we declare it as a final class implementation of driver A interface. Driver B gets that dependency. And it turned out that the compiler was able to optimize those virtual function calls away, so to devirtualize them, which gained us quite some performance benefits. Yeah. So in the end, that simple approach of using the final keyword at very specific places turned out to be a quite nice solution for our situation. Yeah, maybe some of you already did something quite similar. I'm interested to get your feedback or your impressions. Of course, adding final prevents you from inheriting further from driver A, but in our situation that wasn't of any concern. So at the current point of time, we're quite happy with that solution for very specific implementations. But yeah, I'm interested if you have already came across that pattern or if you're using it. I'm glad to hear about it. Yeah, so here again we can see even in that simple example it was devirtualized. Yeah, and thanks a lot. That was the short way of how to of how we could use that keyword. Yeah. So there's a question: is the final behavior defined, or is this a by result of the compiler? So I'm not sure, Mike, if I got your question right. Is this final behavior defined? So you mean if this is compiler specific or if it's standards compliant, right? So in our case, so I can't say for sure. I think it's compiler dependent. We are using currently GCC version 9.3 for some reason we are stuck to that compiler version. We're using optimize level 03, and there it turned out it really made a huge difference on the runtime. Yeah, how are we preventing regressions? That's a good point. So in our application, that's also a safety relevant aspect, and here the regression, we are monitoring our runtime for that critical part during operation. So we would directly see, and the impact was quite massive. About we were roughly 40 to 50% faster in that interrupt level, and we would directly see that on our runtime monitor. So we could see it, but as I get the answer, it's compiler specific, I'm quite sure, and I would expect that behavior to be just an additional hint for the compiler. There won't be any additional class inheriting from our driver A in that example. So whenever you see driver A, you can be sure there's no further inheritance. So it's just an additional hint to the compiler, as I would say, to maybe trigger some additional optimizations. And in our case, we could benefit from that one. Yeah. Yeah, the question link time optimization, if that might result in the same result, we were testing that in advance, and it wasn't the same result. So even with link time optimization activated, those devisualization did not happen in our case. So it's surely case specific whether maybe LTO can already gain you such optimization, but maybe having a final implementation might be worth a try. Yeah. Okay. Yeah, thanks a lot for the questions. Any further aspects? Okay, yeah, great to hear that some of you might also just try it out. Yeah, I think it's not always a recipe to use, always at final, but if you have very performance critical elements and still want to have that abstract base class for example, for that reason, as I mentioned, it might be worth a try. Yeah. All right. Thanks a lot for your attention, and have a lot of fun. Still have a lot of fun. Thanks. Bye.